So the reason you want to scan across all wavelengths of a single solution is so that you can find the optimal absorbance reading. You find the reading that has the highest wavelength. Once you do this, this is your optimal lambda max. This is then going to be your wavelength you use to scan all other solutions.
The Beer-Lambert law assists in describing the linear relationship between absorbance and concentration, meaning that as absorbance increases or decreases, the concentration of the solution will do the same. The Beer-Lambert law is represented by the formula A equals epsilon LC. A is the absorbance. Absorbance represents the amount of light that the solution takes in rather than letting it pass through. This can be found using a spectrophotometer. In this experiment, epsilon represents the lambda that Kristen just mentioned. You can find this by scanning for wavelengths. L is the length of the path the light must travel through. In this case, the cuvette is 1 centimeter in width, so the L value is 1. C represents concentration. Concentration is also known as molarity, which is the amount of moles per liter of solution. The concentration is unknown and can be found using equations once you know your absorbance. In order to use the spectrophotometer, you must transfer your dilutions into cuvettes. You will need a cuvette for dilutions 1 through 3, your unknown, and a blank of distilled water in order to zero out the spectrophotometer. Begin by pipetting the dilutions into their respective cuvettes. Make sure not to put too little or too much in each cuvette. Fill them exactly to the mark. Repeat this until each dilution and blank has its own cuvette. Once you have your cuvettes, you are ready to move into the spectrophotometer room. To begin, wipe the sides of the blank cuvette that the light will pass through. Place the cuvette in the scanner, and then close the lid. Then click on 0. Zeroing out the spectrophotometer calibrates it and creates a baseline response. Remove the blank, and now you can begin scanning the rest of your dilutions. Repeat the steps as before. Wipe the sides, place the cuvette in the scanner, close the lid, except this time click read. This will give you your absorbance value for that dilution. Remove the cuvette and repeat until you have all of your absorbance values. Now, transfer your absorbance values into your notebook and return to lab. Clean up your station and then begin calculations in order to determine the concentration of the unknown. In exercise 1, we created dilutions of a 0.2 m copper 2 sulfate pentahydrate solution. We were able to determine the concentrations of the new dilutions by working out the equation M1V1 equals M2V2, with M being concentration and V being volume. We didn't have the concentration of the unknown, so this is where the absorbance values from the spectrophotometer come in. A calibration curve of our values was graphed on Excel, and determined the equation that will help us determine our unknown and concentration is y equals 35.714x plus 0.0239. We plugged in the absorbance value for the unknown, 0.1964 for y, and solved for x, revealing the concentration of the unknown to be 0.0048 moles per liter.